Hey everyone, welcome back. Today we're going to be talking about Bessel's correction. So let's write down the title. So let's explain what this thing is talking about. If you are sampling a bunch of numbers, x1, x2, x3, all the way to xn, independently from some sort of population, then what we have is sample mean. So we can write down the formula for sample mean, and that is x bar equal to 1 over n sum I from 1 to n xi. You can also write down the biased sample variance. So let's write that down, biased sample variance. And this turned out to be Sn squared equal to 1 over sum I from 1 to n xi minus x bar squared. Now here, notice that this is biased, right? Biased means that the expectation of this estimate at the sample level is not the same as the population level. So then what is the unbiased one, right? It turned out the unbiased sample variance is actually to use Bessel's correction. So the formula, what it look like is 1 over n minus 1 summation I from 1 to n xi subtract x bar square. So now the question is, okay, why is this n minus 1? Like, why can't it be n and we'll be done with it? So today we're going to be talking about why Bessel's correction happened to be n minus 1. So to start showing the Bessel's correction, we need an identity for variance. So let's start with that. The identity really looks at the inside of the square term and see what can we do to make that easier. So let's start from summation I from 1 to n, and inside of the summation you have xi minus x bar squared. So how to make this easier? Let's first expand the full square. So you have summation I from 1 to n xi squared subtract 2xi x bar plus x bar squared. Once you open up the full square, you can then distribute this summation inside the parentheses to each of the terms. So how that works is we have summation, this is xi squared, subtract 2x bar. Notice that these are actually constants, right? X bar is an actual constant. 2 is, of course, a constant. So we can write that out. And then we have our sum, xi. And the last term, let's not forget that. That will give you sum x bar squared. So from here, you notice that, okay, so this x bar doesn't really change by I. That's a rounding index. So this n terms here is just n times x bar. So that gives us a little bit of a simplification. And the same term goes here. If all these xi's are independent, then this term in the middle really just equal to x bar n. So let's denote these two things on the right-hand side. So notice that x bar n is summation I from 1 to n xi. And then also summation I from 1 to n x bar squared equal to n x bar squared. So by using these tricks that we just discussed, we can then write out the following. Sum I from 1 to n xi squared minus 2 n x bar squared plus n x bar squared. And then we can further simplify by taking this minus 2 plus 1, right? And that gives us summation xi squared minus nx bar square. So now from here, with that all being said, that could be act as some sort of identity that we're going to use later in our proof to show the Bessel's correction. From here, we can write out the formula of the unbiased sample variance. So let's take a small detour to explain what is going on with the concept of unbiasedness. The concept of unbiasedness, it's saying that if you have a sample that's coming from a population, and then you're taking some sort of estimates, right? Let's say sample mean, a mean is an estimate. Population mean, the mean is an estimate. How do you know that this is unbiased? Well, the expectation of sample mean, if it's equal to the expectation of the population mean, then we say that this is an unbiased estimator. That's the definition, that's how it's defined. So now the question is, okay, how do we understand this statement intuitively, not just mathematically? So imagine you were doing a random walk. Here is who I am. I'm a student. I'm doing a random walk on Chicago campus. I can walk any direction that I want, completely randomly. So here we say we have a random walk on Chicago campus. So let's take a look at the campus level, not just me as a person, but let's take a look at the campus level. Let's say at the campus level, you have 30% of green people. That's the campus level. And then if you take a look at my personal level, a personal walking distance, walking trajectory, I'll be meeting some people along the road. Maybe I meet a green person, maybe not. But if I talk to every person randomly, everybody walking past by me, I talk to them, I should be getting 30% on average of green people. So this is to say that if I talk to everyone I walk past by, I should be expecting 30% of green people because that is the number at the campus level, right? So that's something I would say an unbiased behavior. How do you know it's unbiased? Well, I don't have any prior knowledge, right? I talk to everyone. So I'm expecting a number that's 30%, which is exactly the same as the campus level. Now, let's say I have a little bit of a bias. Let's say I only talk to green people. Maybe I'm a green person. Maybe that's where I'm coming from. And there's a language barrier, there's a culture barrier, right? So let me use a different color. Let's say due to language barrier, I mostly talk to green people because that's the language I spoke. Other language is challenging to me, right? So what that means is after a certain time, I will probably be having 90% of green people that I spoke to. Now, what's going to happen then is notice that this 90% is going to be greater than supposedly 30% of green people on campus. So since this number is much greater, that means somewhere in my ability, in my behavior of interacting with people on campus, it's not random. It's subject to certain changes, subject to certain bias. And in this case, perhaps the bias is a language barrier. So coming back to this graph up here, that means there are certain direction of the walk I do not take, right? I don't walk to here to talk to this person. I walk to there. Maybe they're green people, I walk to them more often. So some of these paths, they disappear. And you're only taking on paths that I felt comfortable because I speak that language. There's no language barrier. So this is when I say you do have a bias. Whereas if you do your random walk and on the right-hand side is 30% on an individual level, on a campus level is also 30%, then this is what we will say unbiased. So hopefully this gives you the intuitive understanding of why we want to establish this mathematical statement. And that serves as the fundamental key approach for us to explain the Bessel's correction. So we want to know the expectation of that, because that is how we know if something is biased or not. So we start with expectation of s squared, and that equal to expectation of the sample variance, which is 1 over n minus 1 sum I from 1 to n xi subtract x bar square. Now what this saying is, it's the unbiased estimate, because on the right hand side it's a sample variance, on the left hand side it's a population variance, and the expectation of population is the same as the expectation of the sample variance. This is what it means when we say something is unbiased. That is the definition. So by definition, when we say something is unbiased, we can write this kind of formula. And the goal here is to show that this formula holds. And if we can show that this formula holds, meaning that we do something, right, whatever derivation that we're going to do in the end, if this thing equal to sigma square, then we know that this formula here with the justification of n minus 1 indeed give us the correct answer, which is the population variance. So now the remaining work is to fill up the blank, whatever that is, however hard the derivation is, comes down to this sigma square as its result. And if we show that, then that means this n minus 1 correction is appropriate. So let's try it. What's happening here, right? We need to first take the n minus 1 out, and then inside of the summation, perhaps we can factor the expectation inside and rearrange it, and then see if we can make things easier. So first thing, let's move the factor outside of the parentheses. So what that means is it gives us 1 over n minus 1. And then let's copy down whatever we have left. Expectation of summation I from 1 to n xi. And then here we are left with minus x bar square. Now, this is when we use the useful identity that we just derived above, right? We're going to do all the work. We're obviously going to use it somewhere. And that's where we use, right? Notice that here we have this xi minus x bar square. Here we have xi minus x bar square. And then we have a summation. We have summation. So these two terms are exactly the same. And we've gone through all this work to simplify to look like that. Then we're just going to plug in here. So here we say plug in a green star, right? That's what we just derived. Now I can happily erase all these junk in the middle, and I can replace it with summation I from 1 to n xi square subtract n x bar square, parentheses. Now from there, it makes my life easier. I can then factor this expectation inside. And that is to use the linearity of expectation. So let's write down that trick here. This is to use the linearity of expectation. So how that works is 1 over 1 n minus 1 summation I from 1 to n expectation xi square subtract n expectation x bar square. And then let's not forget the bracket, just like that. Now from here, we're one step closer to the truth. Now the interesting thing here is notice that there is another identity. So the other identity, let's write that down here on the right-hand side, is the variance of x. That could be written as expectation of x squared subtract expectation of x parenthesis squared, which also practically means that expectation of x squared equal to what? You move this term to the left-hand side, right? So what is that? That becomes variance of x plus expectation of x parenthesis square. So these two are useful identities for us to carry on the derivation. So let's continue. So what does this become, right? This factor in the beginning, that doesn't change. So that becomes 1 over n minus 1. And then inside of this big bracket, let's do something a little bit carefully, right? Let's work out the first term. Now we said that the expectation x squared equals to this whole thing, right? And this expectation x squared happened to look like this first term. Okay, so that makes our life easier. Well, we just copy that in here as a first term. Great, so let's do that. Summation I from 1 to n, and then here is a lot of copying, right? Parenthesis, variance xi plus expectation xi parenthesis square. And then we're not done yet, right? Notice that here we have a subtract and we have another term, right? And then if you look carefully to the other term, this is the other side of the identity, right? Specifically, we're talking about expectation x squared. So for here, in the second term, we actually have x bar. Now, that's no stranger because you can just add x bar here and identity stays the same. So let's continue. Here we have subtract n, parenthesis, variance x bar plus expectation of x bar, parenthesis, square, close big bracket. So that's what we have so far. Now from here, things about to get very interesting. So let's take some notes of how we can simplify these complicated terms, right? For example, if you have x1, x2, to xn, let's say these are random samples coming from a distribution with some sort of mean mu and variance sigma. If that is the case, then it follows the following. Expectation of xi is going to be mu, whereas variance of xi is going to be sigma squared. Another identity is the expectation of x bar actually is also mu, whereas variance of x bar turn out to be sigma squared over n. Now, these identities based on this premise in the situation is standard concept from statistics. We're not going to derive all these in this video, but we're going to use these as useful identities so that we can make our equation here a little bit easier. Because right now, this is a little bit complicated to read. So the goal is to borrow the identity to make it easier. So let's do that. Let's plug in some of these numbers so that we can replace these difficult jargons. The good thing is that this 1 over n minus 1 stays the same in the beginning. Now, here's when things get really interesting. The sum stays the same, so let's copy that down. That doesn't change. Notice that here is a variance, and here we have an expectation of xi. The variance is just a sigma square. So that is just sigma square. And then you have what? This expectation xi, right? That's just a mu square. So plus mu square. And then you also have subtract n times something, right? So what that means is you subtract n times something. The first thing is variance of x bar. Now notice that, what is that? That's sigma squared over n, right? So here you have sigma squared over n. And then what is the next term? That term is just mu squared. So then we are coming down to one final step. And now watch carefully. There's no I here, right? There's no I here. So this term, we can replace that simply with a factor of n. So that gives us 1 over n minus 1 parenthesis n times sigma squared plus mu squared n times sigma squared over n subtract n mu squared. Now from here, it's just simple algebra. So we have 1 over n minus 1 n sigma squared plus n mu squared minus sigma squared minus n mu squared. And that becomes 1 over n minus 1 times. Notice that this n mu squared and n mu squared cancels out because you plus and subtract the same thing. So what you have left here is n sigma squared minus sigma squared, and that becomes n minus 1 sigma squared. Because sigma squared, you can factor that out. So that gives you n minus 1 sigma squared. Now things is going to become very clear, right? So you have 1 over n minus 1 times n minus 1 sigma squared. And these two terms cancel out. And you're left with sigma squared. Okay, so we've gone through all that work, right? We've gone through all that work just to show what? Just to show that this statement in the beginning holds true. So let's do a small recap. What is happening? So what we have just shown is we've shown that the expectation of population variance is equal to expectation of the sample variance. And why do we want to show that? The reason we want to show that is because that is a definition to say something is unbiased. Okay, so let's write that down in plain English. The expectation of population variance is the same as expectation of sample variance. And we did show that, right? Because throughout the derivation with this correction term, n minus 1, we're able to show that this thing, in the end happened to be sigma squared, which is exactly the variance. It's not some other weird term that doesn't equal the variance, right? It's exactly variance itself, which means this equation holds true, which means what? This n minus 1 correction is appropriate. So let's write that down, the final conclusion, which implies the n minus 1 correction in the formula of sample variance is appropriate. And there you go. Hopefully this convey you the idea why the Bessel's correction is important. And with that being said, hope you liked the video, and I'll see you in the next episode.